Hello, Math 30-1. So this is where we put all what we've learned in lessons 1 to 4 together. Why are we dividing? Why are we looking at the factor theorem? And we are now going to factor some polynomial expressions. And specifically, we're going to factor polynomial expressions that are bigger than what we did in Math 10. In Math 10 and even Math 20, we worked a lot with quadratics, and we should really be real experts in quadratics. If you look at the two little quadratics I have over here, we know that a simple trinomial has a sum of 5 and a product of -6. That's easy. I can just factor that as x plus what we have here, x plus 6 and x minus 1, and that would factor. And when we had tough trinomials, those were pretty straightforward as well. We could use decomposition, or we might use guess and check, but we definitely can factor things like this as well. So if I did the sum of 1 and the product of -30, we would say, okay, well, I know the numbers for that. That's going to be 6 and -5. So now we go 2x squared plus 6x minus 5x. Thank you, Evan, minus 15. And now I can take a 2x out of the first two and I get x plus 3. I can take a -5 out of the second two and get x plus 3. I have a common factor of x plus 3 times 2x minus 5. So we know how to factor quadratics really well. But how are we going to factor things in Math 30 that have up to degree 5 or more? Right? How will we do that? In this particular lesson, we'll focus on factoring polynomial expressions where the leading coefficient is 1. So what they're saying here is we're going to factor things that have, for example, a 1x to the 5 plus 3x to the 4 minus 3x cubed plus 2x minus 1. What if we factored that? But as long as the lead coefficient of the highest degree term is a 1, how will we factor those things? We're going to need to know all the skills that we've done before, plus the things we've learned with factor theorem. So clearly from a graph, if I looked at the graph of a quadratic, we know that the graph has x-intercepts, and this particular graph has x-intercepts of obviously -2 and +3. We can see that. When we factor it, we can see that it has zeros of -2 and +3. And if, like we did when we talked about quadratic equations in Math 20, when we look at that quadratic equation, we can see that that quadratic equation has roots of -2 and 3. So it's just clarifying the words that we've used with those different concepts along the way. So fill in the following blank and come back. So as you saw in the last example, the zeros, the x-intercepts, and the roots of the course are actually the same numbers. But they are talking about different things, but they are the same numbers, just different concepts. So in this one, we're talking about a polynomial, so we'd talk about x-intercepts or we'd talk about zeros. So this polynomial is a function, so we don't say it has roots, but it has zeros of x equals -8 or x equals 3. What do you notice about those numbers and the constant term at the back? Well, clearly when you multiply those factors together, they go together to make -24. So we might say something like the product of zeros gives the constant term. And that's going to be key to us describing what we need to do to factor big degree polynomials like that x to the 5 up there. So when we look at this polynomial, it's already been factored for us, right? It's been done. And what do you notice about when you multiply these the zeros of this together as well? What happens there? What do you notice about those zeros? So clearly the zeros of this were 2, 1, and -1, and those come from the factors. The The important part of that is those come from the factors. If you look at these coefficients that gave you the zeros, and that's really the word we should be using here. When you look at those coefficients of those factors, not the zeros, -2 and -1 and +1, when you look at those coefficients, when you multiply those together, the product of those coefficients, and I know that seems like a change, but the product of those coefficients of those factors gives the constant term. And so that's going to be important. I mean, obviously, if I need to have a +2 right there, these numbers here need to multiply together to give you +2. When you go to expand those factors together, that's where it comes from. Just like x times x times x is x cubed. So that's going to be key for us finding out what we need to do. So in the next example, it's just putting this together into a fancy theorem. So the integral zero theorem, which states that the zeros of an integral polynomial with a leading coefficient must be factors of the constant term. So in other words, if there is a -6 at the back end, you know, because it's degree 3, that there's got to be 3 factors that lead to that polynomial. Now we don't know what they are because we don't have rules. We didn't learn that yet, but we know that there must be an x, an x, and an x to give you x cubed. Now when you look at the numbers that give you -6, it could be, I'm just guessing, but it could be a -1, it could be a +1, and then it would have to be a -6 at the back. Now, I'm just guessing right now, but that's a possibility. This is a possible set of factors that could be that, because we're aware of this integral zero theorem. The only way to get a -6 at the back is to have a product of 3 numbers that gives you a -6, and x minus 1, x plus 1, and x minus 6 could do that, right? So the integral zero theorem says that the zeros of p at x must be factors of -6. So it must come out to this list. I could have ±1, ±2, ±3, or ±6. That's the list of all the potential zeros for that polynomial because of the fact that there's a constant term of -6, right? So rather than do exactly the same one that they had there, we already listed those, right? So what if I had, let's make this something crazy like 24, right? Obviously, this answer is right up here. So if we had x cubed minus 7x minus 24, the possible zeros, maybe 24 is too many. Let's do 15. Okay, so if I said -15, the possible zeros would be ±1, ±3, ±5, ±15. Those would be all the possible zeros of that factor of 15. So what are the possible factors that could come out of that? Well, we could have x plus 1 and x minus 1. We could have x plus 3 and x minus 3. We could have x plus 5 and x minus 5, and we could have x plus 15 and x minus 15. Those are all the possible factors that you could have for that. And you have to pick 3 of them that would work out, right? So if Nicole and Luke go back to their work with factor theorem and the work that Sierra did, they would know that I could test all those things. I could test to see which one of those actually are factors. And so, for example, if they started off, and remember from up above here, if we actually go back to our actual example, they're dealing with this x cubed. So they're dealing with the x cubed minus 7x minus 6, right? So their possible factors were x plus 1 and x minus 1 and x plus 2 and x minus 2 and x plus 3 and x minus 3 and x plus 6 and x minus 6. They're dealing with the original question, right? So they started testing them out. They tested them out. So they plugged in 1 because they wanted to try that as a factor. Whoa, and they didn't get 0. Now those of you that did the factor theorem, you'd know that that's not a factor. Okay, and that's how we want to write our work. So then they do another test and they try x plus 1 and they found out that that was 0. That's a good thing, therefore it is a factor. So we'll put a happy face, and this is obviously not a factor, so that's blue. Okay, And as soon as they found out it was a factor, what makes sense is that we would divide that out. So they divided that out as a factor, just like you would. If you had 24 and you knew that 2 is a factor, you'd divide it in there and you'd get 12, because you've got one factor. They're doing the same thing here. They divided x plus 1 and they got this quadratic and the remainder of 0. If you tried x minus 1 as a factor, you'd see that you got a remainder 12, and that wasn't a factor, right? And in each of Nicole's and Luke's work, one of them is using the factor theorem, and one of them is just using synthetic division, right? So taking the work they've done, what can we do with that? Well, the fact that they now have one factor, if I use the work that Luke did, I now know that my original x, whoopsie, gotta go back and find the question. So I want to present this as I would a Math 10 student, just like we did up here when we were in Math 10 and doing prime factorization of numbers, right? So I've learned that x cubed minus 7x minus 6 now factors because x plus 1 is a factor, and the other factor that goes with that is x squared minus x minus 6. And just like you would with 24, once you knew that 24 was 2 times 12, now you can say that 2 times and 12 is really, you might say, well, that's 2 times 6. And then you carry on, and that's really 2 times 2. And 6 is really 2 times 3. And you're down to the complete prime factorization because you can't go any farther. We would do the same thing here. I now have one set of factors. I'm now at a quadratic. I go back and use my Math 10 skills, and that's really x minus 3 and x plus 2. And I'm down to degree 1 factors, and that's as far as I can go, all right, using the factor theorem. We carry on to example 2. Again, follow through with the strategy that's followed there, and then you're going to complete example 3 by yourself, right? So the first thing you need to do is list the possible zeros. So if I list the possible zeros here, I have 12, so that would mean that I should have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. I have to divide out at least 2 factors so that I can get down to something like a quadratic that I can factor. So the first thing I find out is I test out 1, and I tested out p at 1. And if I plug in 1, I got 0. And what does that mean? And I want you to show your notation like this. So if p at 1 gives you 0, then you write a little statement beside it. Then x minus 1 is a factor, okay? And once you know that x minus 1 is a factor, you go and you say, oh, I will divide it out, right? I will divide by x minus 1. And when I divide by x minus 1, I get this as my quotient, and this is my remainder. And if I didn't get 0 as a remainder, then that wouldn't be good, right? So I want to carry on now. So now if you follow me over with this quotient statement, now you can come up to here and realize that, okay, my polynomial that I used to have, I've now factored this polynomial right here into a factor of x minus 1, and this is my other factor of x cubed plus 3x squared minus 4x minus 12. And you could either use the factor theorem if you really wanted to, but you're supposed to remember your stuff from Math 10, so you'll notice that if I look at that cubic, that's actually something that can be grouped. And I don't feel like using the factor theorem if I don't have to, so I will group that, and I will take out an x squared out of the first 2 terms and a minus 4 out of the second 2, and then clearly I get common factors. So now I get 3 factors of x minus 1, x plus 3, and x squared minus 4, and I can factor that by doing a difference of squares. So there's my completed factored form in part B. What are my zeros? My zeros for that question are obviously 1 and minus 3 and 2 and minus 2. state the zeros for that question, 1, 2, -2, and -3, because obviously they're the same, right? So that's using the factor theorem to completely factor a degree 4 polynomial, okay? Now, not everything turns out to be super duper nice questions, okay? Sometimes they don't turn out to be all integers, as you can see right here, okay? I'll let you play with your graphing calculator. I don't think I need to do that for you. You can do that. I'll put the answers there. I'm going to go straight to using the integral zero theorem and synthetic to determine exact values, because Math 30-1 really isn't about graphing calculator. It's about algebra. So if we start off, let's just do our strategy. So how would I do this, doing it algebraically? Well, I don't have many possible zeros, so I'm just going to write, and this would be the work that you have to support your algebra with. So what are my possible zeros? I'll write PZs, and they're just simply plus or minus 1. I only have 2 options. Okay, so now I'll simply check one of those. Using factor theorem, I'll plug in P at 1. And if I plug in P at 1, I get 1 minus 3 plus 1. That ends up being minus 4, so clearly that means that it's not a remainder of 0, so that's not a factor. But what if I plug in P at minus 1? Well, P at minus 1 gives me minus 1, minus 3 plus 1. That does give me 0, and please make sure you write stuff like this. Therefore, you now know that x plus 1 is a factor. So now, do a little dance. Now you know that you can break this up into 2 factors. One of them, okay, so I'm going to put it down there. One of them is P at x equal to x plus 1 times something else. And what is that? Well, you're going to have to use synthetic division to find out that other factor. So I'm putting a plus 1, and then I've got 1 minus 3 plus 1. Bringing that down 1 minus 4, 1, 0. Yay! Okay, so now I've got my quotient, and my other factor is x squared minus 4x plus 1. But you'll notice pretty quickly that Math 10 doesn't help you with that. You can't factor that. And you certainly aren't going to use your graphing calculator. So now you have to say, well, if I want to know the exact value of my zeros, I'm going to have to use the quadratic formula. So taking this part right here, I say that x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. And that means that I get positive 4 plus or minus the square root of 12 all over 2, which equals 4 plus or minus 2 root 3 all over 2, which equals 2 plus or minus root 3. Therefore, the question was about finding the zeros, and therefore my zeros are minus 1, 2 plus root 3, and 2 minus root 3. Those are the zeros for this particular polynomial. And if you want the decimal versions, I think you guys can probably handle that with your calculator. But to 2 decimal places would be minus 1.00 and 0.27. Okay, complete the assignment for lesson 5.